Welcome to the AI Research Roundup. I am Alex. Today we explore UniVLA, Learning to Act Anywhere with Task-Centric Latent Actions, a paper from Papers with Code, published May 9, 2025. UniVLA presents a new framework for Vision Language Action Policies, or VLA policies. These AI systems help robots understand instructions, see, and then act. Its key is a latent action model, learning essential action features from diverse videos. This enables UniVLA to generalize across different robot physical forms, known as embodiments, and various environments, using even human videos, all very efficiently. And it's great to see they've also released the code for this work. So over on GitHub, you'll find the official UniVLA implementation. This includes pre-trained models, and all the scripts and guidelines for training, evaluation, and even deploying it on real robots, which is pretty comprehensive. Alright, so a key part of UniVLA is its use of what the paper calls task-centric latent actions. Latent actions are essentially compact, learned representations of what a robot needs to do, derived from videos without explicit action labels. Think of them as high-level instructions, like pick up an object, rather than very detailed joint movements. UniVLA learns these task-centric latent actions to capture the core essence of a task. Now, to test how well UniVLA performs with these task-centric latent actions, the researchers used several benchmarks. A benchmark, in this context, is a standardized set of tasks and datasets used to evaluate and compare the performance of AI models. Figure 4 here shows some examples from one such benchmark, called Libero. We see different task categories. Libero Spatial, with unseen layouts. Libero Object, with novel objects. Libero Goal, with different objectives. And Libero Long, for complex, long-horizon manipulation tasks. UniVLA performed very well here. Alright, beyond those simulated benchmarks like Libero, Figure 5 here takes us into real-world robot experiments. We can see the robot tackling 4 different manipulation tasks: store the screwdriver, clean the cutting board, fold towel twice, and stack Tower of Hanoi. The bar charts on the right then really drive home the point, showing UniVLA in blue, achieving a substantially higher average success rate and average score compared to other methods like diffusion policy, OpenVLA, and LAPA. This performance uplift in these practical, real-world scenarios is quite significant. Okay, so shifting gears from manipulation, Figure 6 here looks at a navigation task. This bar chart shows the Oracle success rate, which in these navigation tasks essentially measures how often the model correctly identifies the goal when guided along an optimal path on the R2R benchmark, specifically within the vision and language navigation in continuous environments, or VLNCE. UniVLA, in blue, hits 47.1%. What's really notable is that it achieves this high success rate using only a single image frame as input, putting its performance nearly on par with Navid, which uses all historical views, and well ahead of OpenVLA. So we've seen UniVLA's strong performance on navigation benchmarks like R2R. Now Figure 9 here really underscores an important aspect: its data scalability. This radar chart shows performance across those real robot tasks, the R2R navigation benchmark and the Libero manipulation benchmark. The key thing to notice is how performance, represented by the expanding colored areas, improves as more diverse data is used for pre-training. Starting with just Bridge V2 data in yellow, then adding OpenX data in green, and finally incorporating human videos in blue, we see a consistent boost in scores across all 3 task types, highlighting UniVLA's ability to effectively leverage varied data sources. Okay, and building on that idea of learning from diverse data, Figure 8 here gives us a closer look at what those task-centric latent actions actually represent. We see 3 groups of actions: pick up things, place things, and move forward. What's really cool is that each row shows the same learned latent action being recognized across completely different datasets and embodiments, from various robot platforms like Bridge and RT1 to simulated environments like Libero and even human videos from Ego 4D. This demonstrates the semantic consistency of these latent actions, meaning they capture the same core meaning regardless of the source. So we've seen these latent actions are semantically consistent across different sources. Now, figure 10 here really drives home another key benefit of UniVLA. Its remarkable data efficiency. We're looking at two line graphs, for libero goal on the left and libero long on the right. The horizontal axis shows the percentage of training demonstrations used from just 10% up to the full dataset. UniVLA, shown by the green line labeled hours, achieves very high success rates even with very little data. For instance, on libero goal, it hits 86.3% success with only 10% of the demonstrations, significantly outperforming other methods like OpenVLA and even the previous state-of-the-art. So to wrap things up on UniVLA, it's really shown us how learning these task-centric latent actions can lead to impressive data efficiency and, crucially, the ability to generalize across very different robots and environments. This is a big step, I think, towards AI agents that can learn more broadly and adapt to new situations much more easily. Well, that's all the time we have for today's AI Research Roundup. Thanks for tuning in, and I'm Alex, signing off.